All right, we're taking a look at number 22 from the text, since so many of you asked about it. So what I've done here is, our situation is we're trying to figure out if, we were asked to figure out if the normal force provided by the road was enough to keep the car on a banked curve. So basically what I've done is I've already started my free body diagram, or started my guesswork with my free body diagram and with my givens, and I saw that the velocity or the speed was in kilometers per hour. So I just set up my conversion to get that in meters per second, because since we're talking about force that's going to be measured in newtons, I need everything in the MKS system: meters, kilograms, and seconds. So with this, the next step I would take is, since we're asked, the question is specifically asking us, will a friction force be required? So the first thing I would do is I would figure out exactly how much centripetal force it's going to take to keep this car on the road at that speed. So remembering that centripetal force equation is mass times the tangential speed squared divided by the radius of the curve. And I know that the mass is 1,200 kilograms. That tangential speed was 26 meters per second. That quantity is squared, divided by radius of the curve, which in this case is 67 meters. When I do all that, I end up with 1.2 times 10 to the fourth newtons. So that's how much force it would take at that speed to keep the car on the banked curve. Now, what I'm going to do is I'm going to redraw my free body diagram. I'm going to get all that other junk out of there. So I've got the normal force, I've got the weight force pulling down. That centripetal force is going to come from the x component of the normal force. There's a piece of that normal force that's pointing back into the center of the circle. All right? So I go to, once I've done my free body diagram, I'm going to go ahead and do my force summation according to Newton's second law. Since that car is not accelerating either up or down on the track, it's staying in a horizontal circle, that tells me that the net force is 0, and that the force depends on, that net force depends on two forces. It depends on the vertical component of the normal force, which, since that's my angle, is going to be determined by, and it's the adjacent side, that's going to be determined by the normal force times the cosine of the angle. In the other direction, down, we have the weight of the vehicle. And what I'm going to do is, out of all this, I'm going to go ahead and set up to solve for the normal force. When I do that, I end up with just adding that to the other side, dividing by the cosine. I end up with the weight of the car divided by the cosine of the angle. That should give me the normal force. Now, let's do the same thing for the x direction. In the x direction, there is an acceleration because that object is kept in a circular motion. And so that's going to be, in this case, going to be due to this component of the normal force. And since that is the opposite side, that would be the normal force times the sine of the angle. And in this case, that's the only force acting in that direction. Which, since I've already figured out the normal force up here, I'm just going to substitute that in, and that gives me mg over cosine theta, because that's the normal force, times sine theta. And then using my trig identities, I have sine over cosine, so I can simplify that even farther to mg tangent theta. Then it's just a matter of plug and chug. I've got to plug in my values. Mass is 1,200 kilograms. Acceleration of gravity, 9.80 meters per second squared. Tangent of 12 degrees, which gives me a total of 2.5 times 10 to the third newtons. So that's the force being supplied towards the center of the circle from the normal force. As you can see, not even close to enough. So we are going to have to take friction into account. So I need to set up a situation now where I'm taking friction into account. I'm going to redraw my free body diagram. I still have the normal force acting perpendicular to the surface of the road. I still have the weight pulling down. However, now I have a friction force that is pointed parallel to the surface. So since the road is angled, since it's banked, my friction force is actually going to be in a direction like so. There's my x-axis, there's my y-axis. I go back to my force summations again. All the forces acting in the y direction, it's still not accelerating either up or down, so the net force is 0. And it consists of two forces. It consists of the segment of the normal force that's in the vertical direction, so that'd be the normal force times the cosine of the angle. In the other direction, in the y direction, actually there's two other forces because there's a segment of that friction force that's also going to be pointed in the negative direction. And since the angle subtended is there, I'm looking for the opposite side, so that would be the sine of the angle. And then also pointing down is still the weight of the vehicle. Once again, I'm going to want to solve for the normal force. So when I do that, I'll go through a couple steps here. All I'm doing is just rearranging by algebra. Plus that. And then again, I need to get that by itself. Divide out the cosine on both sides. So the normal force is going to be equal to that plus that divided by that. Turning my attention to the x direction now. I do my force summation in the x direction, which now that there is a portion of that is going to be causing a centripetal force because the car is staying in a circle, in a circular motion. So there's a centripetal force pointing in toward the circle, which can be found with mv squared over r again. And that is the result of two different forces. It's the result of the horizontal segment of the normal force and it's also a result of, now we've also got the horizontal component of the friction force. So then what I need to do, and this is where it gets fun, is here's my value for the normal force. We've got to take this and we got to plug it into there. So that is set equal to that whole mess times sine of the angle, and then still added to that. All right, now we've got the job of we've got to find the friction force, because that's what we're ultimately asked to find, to solve for. So we've got to set to work on this. So first thing I need to do is I got to get rid of this denominator. So I need to multiply both sides by the cosine. When I do that, I end up with this plus this times sine of the angle. Again, just following through my algebra here. And since I had to multiply that by cosine, that's going to be cosine squared theta. And all of that is going to be equal to that also times cosine of the angle. So there's my expression that I still need to simplify. So I'm going to go ahead and expand this. So I end up with that times sine squared of the angle plus mg sine of the angle plus, then this doesn't change, force of friction cosine squared equals mv squared over r cosine theta. Next, I'm going to isolate these terms because they both have the friction force in it that I'm looking for. So I'm going to end up with force of friction times sine squared theta plus force of friction cosine squared theta equals mv squared over r cosine theta minus this term over here that does not have force of friction in it, mg sine theta. And then now I can factor this out, and those of you who remember some of your trig values and functions might start to recognize something here. I'm going to end up with sine squared theta plus cosine squared theta is equal to all of this over here, mv squared over r cosine theta minus mg sine theta. You might recognize all this. There is a trig identity that says that sine squared plus cosine squared of an angle is equal to 1. Thank goodness, because that reduces that whole term to 1. So now I'm multiplying force of friction times 1, and that is equal to the rest of this term. And then from there, it's just a matter of plugging in the values and finding your answer. So, hope this helps, and we'll see you in class.